gauge fixing. And at the end, what we really came up with as one of the major conclusions here, or like one of the major things that we discussed, is that gauge invariance, or in the particular case of U1 symmetries, we've discussed that explicitly. Gauge invariance in a system that contains a gauge sector, but also a scalar sector, and they talk to each other through gauge interactions. The implementation of gauge symmetry is consistent there with a large vacuum expectation value of the scalar field. So when we talk about spontaneous symmetry breaking of gauge symmetries, what we really mean is realizing gauge symmetry non-linearly in a way that's consistent with vacuum expectation value of the associated scalar field. Okay, so then we saw that we have these mixing terms between the vector particles and the derivatives of the Goldstone field. So those were the ones that transformed non-linearly under the gauge symmetry. So mass terms are automatically forbidden. So we deal with essentially a massless vector field that couples directly to the derivative of a massless scalar. And I said that these are terms that we don't really like, okay, or they sort of hamper our traditional idea of gauge theory in a perturbative sense. But I got a few questions, so I want to make this point a little bit clearer, okay? So we can draw some analogy here to the pion decay. I'll just give you the Lagrange piece for that. So charged pion, the interaction Lagrangian for that is exactly that. Okay, you have a charged pion that couples directly to a W boson, and you address this with factors of the coupling constant of the weak sector, arbitrary factors of square root 2. So this is not really identical, so I'll just approximate this, and the pion decay constant. Okay, so it's dimension 4 operators, everything's fine. It's not really exact, but what you see is that this really, when the W decays into muons, into a muon and a mu neutrino, then this accounts for exactly the decay width and the decay probability of a charged pion going to its favorite final state. So somehow that's the pion decay constant.
I mean, what letter is that?
That's an F and a pi. Okay, it doesn't really matter. Okay, so the crucial bit here is really that exactly these derivative interactions, they appear in nature, and they appear in such a way that we can experimentally verify them to a high degree. So in a way, we could now say that's pretty much the same thing that's happening here. Okay, so I made a big fuss yesterday about these interaction terms and getting rid of them, but actually in some sectors they show up and they are quite relevant. But here we're dealing really with two different beasts. Okay, so this is really a physical state, whereas this chi here is not so much a physical state. So I want to make this point a little bit clearer, and in order to do that, you can ask the question, why is this gauge fixing procedure really, really relevant? Okay, so ad hoc you can think of a mu, it's a 4 vector, so it has 4 different degrees of freedom, naively, okay? So it's just a 4 vector and 4-dimensional Minkowski space. So if you Fourier transform it, you have to find a 4-dimensional reference frame that you use to span the 4-dimensional space. So, but let's start with the Lagrangian here. So just pure gauge theory Lagrangian U1 case. So what's the traditional way of going from semi-classical physics, like well, purely classical physics really, like Maxwell's theory, which this really is here, over to the quantum picture, is that you promote these fields to quantum operators, okay, and you determine equal time commutation relations, okay? So this is just the canonical way of quantizing a theory. So this is what you do, you just enforce canonical commutation relations between the field and its associated canonical momenta, pi nu. And pi nu is just given by derivatives of this. So let's see if that works out as we want it. So if you just calculate the associated canonical momenta, pi nu, just take the derivative with respect to the time and a nu, you end up with this thing here. So you can already see if I choose the time-like direction of pi nu, so if I said nu to 0, then this thing cancels here. So pi naught will vanish exactly. What that means is that these equal time commutation relations, they can't hold, because a naught is certainly not 0, well, or it can be 0, but it will commute with pi naught, because pi naught is 0, so it will be 0 here on the left-hand side, but it will definitely not be related to some of the delta distributions that I wrote down here. Okay, so this means this is really the end of the day. So either we abandon really our idea of quantizing the theory, or we just abandon the Lagrangian. And because we want to do quantum theory, we probably have to reject the Lagrangian as it is. Okay, so that's not good. But what we can do now is we can modify this guy. Okay, modify it in such a way that we introduce an additional term here, which, you know, we're not doing spontaneous symmetry breaking here, so the A field stays completely massless. So you can compare this to sending the VEF to 0. You get exactly the same picture that we discussed yesterday. And this lambda just relates to this gauge fixing parameter that I introduced yesterday. Okay, just moved it out of the denominator just to get the point across here. So we can modify it like that, calculate the canonical momentum, and it does exactly the job that we want. Namely, if I now set mu to 0 here, so I just look at the time-like configuration of the associated canonical 4 momenta, then I get something that is potentially non-zero because I introduced a term to do exactly that job. Okay, so that's not 0 in the case when lambda is not equal to 0 and d nu a nu is not equal to 0. Okay, so this is quite a departure from classical mechanics here, or electrodynamics. So we can sort of make a meaning or make a first step into quantizing this theory by adding this gauge fixing term with a non-zero value of this lambda, okay? But also we have to sort of require that this d nu a nu does not vanish. So in the following, let's set lambda equal to 1 just to make the algebra a little bit simpler. So because we are promoting these fields now to operators, we have to sort of really worry about how they act on fields. So the first guess is that the usual Lorentz gauge condition that you use in classical electrodynamics, for instance, we can't use this here. So we can't have the box operator, just the d nu a nu, we can't have that equal to 0, but we can still require this to be 0 when it acts on a physical state in the Hilbert space, okay? So this would be like a sort of an educated guess going from the classical picture over to the quantum picture. So let's see what happens. So because now we introduce this this space of states, Fock space, we can argue maybe we are not doing really equal time relations in the operator space, but we do it really as expectation values when evaluated amongst physical states. Okay, so this it's just taking it, you know, as a scalar condition rather than an operator value condition. So if we put this together, then essentially we get something that is rather similar. So you just enter the equal time commutation relations. Okay, the delta distribution is diagonal in this space of states. The psi's, you can normalize them. So you end up with a modified condition. It looks like this. Turns out this also doesn't really work. Okay, so because now we set lambda equals to 1, our time-like direction will be exactly the negative of d nu a nu. And if you plug this in to exactly this piece, you'll see that the left-hand side is also 0. Okay, so you end up again with a contradiction. Not so good. Okay, and the solution, kind of old school here, is really the formalism introduced by Gupta and Bleuler. So instead of requiring that all of these, the entire d mu a mu here vanishes, you just demand that the positive frequencies vanish. So you write down a Fourier transform of this A mu field as you do just for any free field. You have these exponents dressed with positive frequencies and negative frequencies, and you just require that the positive frequencies acting to the right-hand side give you 0. That's of course equivalent, we take the complex conjugate of the whole thing, that the negative frequencies acting on the one form give you 0. Okay? And if you plug these things together, yeah, you just add these two conditions, then you see that the average value of the Lorentz gauge fixing condition is enforced by that. But we are taking it one step more abstract, if you wish. Okay? So what this means now is, if you just look at what d mu A mu means, so you expand this out through the metric here, so you get a relative minus sign. So what this relative minus sign then means for the Fourier modes, and the Fourier modes you interpret them, so the Fourier coefficients, you interpret them as raising and lowering operators, which come about by exactly fulfilling these equal time commutation relations. What this means is that now the modes that are located into the time-like direction of the harmonic oscillators are coupled with the longitudinal polarizations, okay, when you act them on physical states. So this means that when I evaluate, say, the Hamiltonian, or I evaluate the normal ordered Hamiltonian density of a certain system in a physical state psi, what will happen is that the time-like polarizations will cancel exactly the longitudinal polarizations. So this statement tells you that if you're only interested in the physics of such a system, then only the transverse polarizations of the photon field will contribute. Okay, and this is exactly what we want. So what the gauge fixing really does, when looked in the context of an interacting quantum field theory that acts on a Fock space, it really makes sure that you're not overcounting your degrees of freedom. So you deal with two polarizations of the photon field, you better make sure that your theory only admits two polarization states. So you can see that this gauge fixing is really essential to get rid of unphysical degrees of freedom that are ad hoc there in your theory. And this gauge fixing condition here, okay, so if you did that using path integrals and everything, you get, as I said yesterday, you get ghosts that sort of take over this gauge fixing conditions to an effective Lagrangian. Those have wrong statistics, so in a way they act as negative degrees of freedom, just to compensate exactly for the degrees of freedom that naively are there when you deal with a four-dimensional vector. Okay, so you can see that this is really, it's not some trick that we take to make things more easy, just from a calculational perspective, but it really plays a fundamental role in assuring that we deal with the right amount of degrees of freedom here. Okay, and of course, if you do this in a non-abelian case, interactions get a lot more difficult. But I think this just gives you a bit of an idea that gauge fixing is really required in order to come up with calculations or implications that are physical. Are there any questions related to that before we continue? Yeah? Well, the only restriction that we have when you do perturbation theory is that only one solution gets singled out from the gauge group. Okay, so essentially you enforce that condition for each generator. You get one unique solution. So you separate out the integration over the group space into fixing exactly this one solution and integrate over all gauge transformations that relate all other solutions in the equivalence class. Yeah? So this doesn't work in practice. So because there are more than just one solution to say the Lorentz gauge fixing condition. So you have to, if you do non-perturbative quantum field theory, you have to deal with stuffs called Gribov copies. So people on the lattice sometimes worry about that because when field values are large, then you get multiple solutions, multiple zeros of this gauge fixing condition. For us, when we do perturbation theory, this is not relevant. But of course, you can also choose different gauge fixing conditions that are not, Coulomb, or they are not axial, or they are not, Lorentz. But this becomes relatively intransparent if you do it like that. It's much more sophisticated if you do this really in the path integral formalism. Yeah. But in general, it works. But for our purposes, we are just interested really in using the Lagrangian as a tool to evaluate endpoint functions. So you do this in the easiest way to achieve your goal. Yeah?
I think I might be just the commutator relation, it looks interesting to me that it doesn't have to be at the same time. So it's d3 x minus y. They have the same spatial point, but not at the same time.
Yeah, this is because I forgot to put x naught equals y naught here.
Okay.
Yeah, that's, of course, these commutation relations, they're always supposed to be at equal time. So in these quantization conditions, you always seem to violate Lorentz symmetry a little because you're treating time and space on a non-equal footing. But of course, you start with a completely Lorentz invariant Lagrangian, so you'll end up with a Lorentz covariant description. So everything's fine. Yeah, but of course, make sure that you provide the full information. I thought I had done this, but I have it here. So not everywhere. So that's fine. Good. Any other questions? Yeah.
Will you be able to pass it to a Hamiltonian system using the Dirac constraints idea?
I'm not 100% sure. Maybe we should talk about this later. So usually I'm not 100% sure what you mean exactly by that, but very few times you see in quantum field theory classes the quantization of spin 1 fields. You see scalars because they're easy. You see fermions because they use anti-commutating relations between the raising and lowering operators, so this directly relates to Fermi statistics, so that's lovely. And vectors are notoriously difficult because you tend to overcount the degrees of freedom. So and this is why this Gupta-Bloiler formalism is sort of really old school, the first way of, maybe not historically the first approach to quantize this, but certainly if you pick up old textbooks written in there. So this is slightly cumbersome because it relates to this idea that you have to violate gauge symmetry to get rid of the unphysical degrees of freedom. But of course, if you look at this in the broader context of quantum field theory, especially in its realization in terms of path integrals, you see that this is actually quite a nice concept and it comes about naturally. All right. Well, then let's crack on. Just get rid of this. All right, so the last bit we did is we had a look at SU2 times U1 and introduced the Higgs potential that again predicted a non-zero vacuum expectation value of the field. And so our starting point was that we chose a direction of this, okay, of the vacuum expectation value. So, and essentially this value of psi in the gauge fixing accounts for all different rotations that you can, put this V into. It can be completely imaginary, can be in the one direction, and so on and so forth. So this choice is arbitrary, but we fix it at this point. And this gauge fixing in the end will take care of things at the quantum level. So we choose that, and then we know from our U1 example, the mass terms will be generated through interaction terms like this. Okay. So, well, this was the covariant derivative. Also d mu is a d mu minus IGTA WA mu minus IG prime B mu. And TA is just the generators of SU2, so that's the Pauli matrix is divided by 2. So when we plug this in and evaluate the bilinears in the gauge fields for the vacuum expectation value, you obtain terms like this. So you have your E and your B field, and you have this mixing matrix. You have a G squared, G squared, G squared, G prime, G prime, G prime squared. And the same vector here, W and B, mu. Okay, and then to relate, so what, of course these bilinears are mass terms in the fields. This is exactly what we wanted to achieve. And to find the eigenbases, so the mass eigenbases as such, we really have to diagonalize this symmetric submatrix. Okay, and this can be done with a two-dimensional isometry that's characterized by a single rotation angle. And that angle was given through cosine theta w, which is the Weinberg angle, and that was a G squared divided by G squared plus a G prime squared. Okay, and this relates our Z boson and the A field with the old basis in the gauge eigenstates, C theta minus S theta, S theta, C theta. Okay, so the masses that we got, here the eigenvalues for W1 and W2 are just G squared times V squared. Okay, so I forgot the V squared here, so it's a V squared divided by 8. So the mass terms that we get here are later on related really to the mass values of our gauge fields. I wrote them down last time, I'm not going to do this again. But what we found is that this MA is equal to 0, so if we have one massless vector boson still in our spectrum, and that tells us that hidden in there is an unbroken U1 symmetry. Okay, so because we are left with a massless vector field, that tells us there has to be an associated gauge symmetry with it. So this is a unbroken U1, and of course we identify this with quantum electrodynamics that's now embedded into the electroweak interactions. So the associated coupling direction in this SU2 times U1 space is the 3 component of the weak interactions plus whatever quantum number you give it under the hypercharge. Okay, so for instance, in this normalization, the Higgs field was a 2 1/2, 2 minus 1/2, 2 1/2, I think, yeah. 2 1/2. And the associated coupling, which we have to take as the electromagnetic coupling constant, is just given by G times G prime divided by the square root of G squared plus a G prime squared. And this is also a G times S theta, or a G prime times cosine theta. Okay, so whenever you deal with an unbroken symmetry, it's just natural that you express whatever fields you have in terms of eigenfunctions of this unbroken direction. That just makes symmetries as apparent as possible right at the Lagrangian level. Okay, so you don't need to deal with hidden symmetries then when you calculate S matrix elements. So The gauge fields, they transform in the adjoint of SU2. So the W fields, they are not charged under hypercharge, but they form a triplet under SU2. So we look at the triplet representation of T3, and remember that the adjoint is just given by the structure constants of SU2. And none of them are diagonal, right? It's just the anti-symmetric properties of the epsilon tensor that tells you that there's no symmetry, there's anti-symmetry. So if you take now T3 in the adjoint representation, you diagonalize it, then you induce a basis transformation in the adjoint field space, and you will end up with your charged W's. Okay, so expressing W1, W2 in Q states, we end up with a W mu plus minus, just 1 divided by square root 2, W mu 1 minus plus W2 mu times an I. Okay. All right. And of course the B field has no hypercharge, 0, and the W3 component is vanishing in the adjoint representation, so it's 0. So you're just mixing values with 0 effective Q charge, and this is why we have this mixing between these two states here in the first place. Okay, otherwise we would not be able to rotate them between each other. This is actually something that always happens. So everything that's allowed to mix under left symmetries will typically mix, unless you have some additional symmetries that forbids that. Okay, so now we end up with our Lagrangian that now contains G squared B squared divided by 4, W mu plus W mu minus, plus 1 divided by 2, G squared times G prime squared times B squared divided by 4, Z mu plus 0 times A mu. Okay, so the normalizations here are different because W is now a complex field. Okay? And this is a real field, so there's an additional factor of 2 that you have to take into account. So this is the W mass squared, and this is the Z mass squared. W1 plus.
You've got what's the primer of 1 on your W mu and W.
This here?
Yeah, there's.
Where's a
Next to the plus, there's a
here?
little bit down to the left. There's what looks like a dash.
That?
No, at the top of the mu. It's right next to the W.
Oh, this. Oh, that's just because the chalk gave up. Okay. All right, and this is the A mass squared. Okay, so as I said yesterday, something quite funny happens here now. Namely, if you look at so this is the squared of the Weinberg angle, actually. So we have the V squared here, we have the V squared here, we have force here and force here. That's all great. So if we take the W mass ratio and the Z mass, well, the ratio between MW and MZ squared, you get something like a G squared divided by a G squared plus a G prime squared. Okay, so this is exactly the Weinberg angle that we have here as a G squared divided by G squared plus G prime squared. So what we have from this is that MW squared divided by MZ squared is exactly cosine theta W squared, but it's also G squared divided by g squared plus the g prime squared. Okay, so, and this is where we sort of left yesterday, really, when I mentioned that this is quite cumbersome, because normally this cosine theta is an angle that rotates the basis of these W and B fields, okay? And MW and MZ squared, they relate to the eigenvalues in the diagonal representation. Okay, so these two things, ad hoc, don't need to know anything about each other. Okay, so the eigenvalues are not, directly related to the eigenvectors. Okay? They come hand in hand, but it's not the same. Cosine squared is obviously smaller than 1, but you can have mass values that are much bigger than 1 in symmetric matrices. So something interesting seems to happen here. And also, this is a prediction that we can test, because the W mass shows up as a resonance, the Z mass shows up as a resonance. So you measure these values, just take the ratio of them, you get one particular prediction of the cosine squared of the Weinberg angle. But also, if you now express interactions with fermions, we haven't introduced these though, but believe me, we'll do this to some extent. If you express these now in terms of this cosine Weinberg, so you will couple to the SU2 content of these fermions, we'll couple the W3 to, and then you rotate it into the mass basis. So you see that this cosine theta will show up in neutral current interactions, but also in the charge current interactions. Okay. So what this relates to is the ratio of charge current interactions and neutral current interactions, okay, which is a completely different thing than just mass values. So you can go to LEP, say, and people have done that. You measure these charge and neutral current interactions to very high precision, and you compare them to the mass values that are known from UA1 and UA2, for instance. And you see they are bang on, okay, and so different observables here are related, and this can only be the case if there is some additional symmetry in place. So, and how this happens is actually that there's more symmetry than we demanded, really. So how can this be? And this is a nice exercise in group theory, really. So we broke electroweak symmetry here really with a doublet of SU2. Okay, and the doublet of SU2 has this additional feature that it's actually symplectic. Whoops. So this means is that 2's of SU2 are symplectic. So what does that mean? It means I can define a, what this means here really is that the 2 is equivalent to the 2 bar configuration. Okay. So you take the charge conjugate of your Higgs field, and that will transform exactly like the 2 itself. So the charge conjugate field is defined as I sigma 2 times the complex conjugate of the Higgs field. And this is essentially just the two-dimensional epsilon tensor, if you wish. Okay, so so this phi c transforms exactly like phi. So actually, we don't really know whether we are dealing with phi c, or linear superposition of phi and phi c. Okay, so to this end, and to make this explicit, we can Do you want me to show this? Why? How this comes about? Or do you want to have a? Or do you want to have a crack at it as a homework?
I love this idea that we have any time to do actual homework assignments.
That's a weak argument, okay? There's nights. No, that's okay. I mean, we can do it here together. Okay, so you have to use a few tricks that I have hidden here. Okay, so if you think about phi transforming as that, so linear transformation, and every u that is element of SU2, you can write this as a 2 by 2 matrix, obviously, with entries A, B, minus B star, A star, with the additional condition that A squared plus a B squared is equal to 1. Yeah. So that's the Cayley-Klein parameterization, and this is where you realize, okay, SU2 is just the free sphere, and so on and so forth. So it's topologically nice and has no holes, and it's a universal overlapping group of SO3, for instance. Okay, so if we now look at phi c here, so we just take the complex conjugate of everything. So we know that phi star will transform as a u star times phi star. Okay. And now we dress everything with I sigma 2s on either side. I sigma 2 u star. And because this is the epsilon tensor, and the square root of the epsilon tensor is just a unity matrix, or related to the unity matrix, if you sneak an additional minus sign, then you can write this as a sigma 2 times I sigma 2 times phi star. Okay. So now, if you take this representation of u star everything, then you multiply through these I sigma 2s, you'll see that exactly this operation by multiplying these I sigma 2s with the relative minus sign will reverse the complex conjugation that you have induced here. So if you do that, you'll see that this will actually be exactly like an A, B, minus B star, A star, phi c, okay? Which is just our u. Maybe if you have some time on your hands, you can try to break electroweak symmetry with a triplet. So you take the Higgs field as a triplet on the SU2, and you break it like that. And what you will see is that actually you will not get a mass ratio like this, okay, but you will get a mass ratio that has a factor of 2 somewhere hidden here. Okay. So just by looking at the mass ratios of essentially UA1 and UA2 discoveries and compare it to Lab 1 and Lab 2 measurements, we know that electroweak symmetry breaking has to happen really through mostly a doublet. Not quite true, because you can play some tricks with complex triplets. You can add a real triplet to the game and pretty much reinstate similar symmetries to sort of protect this additional symmetry that we're dealing here with. So now that we've seen that essentially we have this phi c, this charge conjugated scalar field, we can reveal this extra symmetry that that I was alluding to.
Sorry, what was it that indicated that there's additional symmetry?
We'll do that now. Just give me. No. I make comments all the time, but.
I need to follow this. What was the upside of this?
So, give me a second. Okay. So. Yeah. So what we see here is that phi c. So if I transform phi with a u, I can equally look at phi c and transform that. So now I can look at the superposition of phi and phi c and interpret this as my new phi. Yeah? And these are then a 2 by 2 transformation between two states. So hidden in here is an additional SU2 symmetry. And because I will not change the norm, these things, so let's make that a bit explicit. Alrighty, so for this, so because now phi C and phi transform similarly, I can define a new field, and I call H, and that's a 2 by 2 matrix that contains now phi C and phi. Okay. So we saw that the potential was really just a function of phi dagger phi. So I want to express phi dagger phi now as a function of H. And if you do that, if you want to do that, you'll find that this is exactly 1/2 the trace of H dagger H. And essentially there you have your new symmetry. We're not talking about gauge symmetries here. We can only look at this from a global perspective. Then this is completely invariant under transformations where you send H to UL, H times U dagger, okay? Trace is cyclic, we just pop that in. Just do cyclic permutations and you see all of these ULs and UR daggers, they just get absorbed. And really two different SU2 matrices here. Of course, UL will identify as weak isospin, and that will be gauged. And hypercharge you can think of as being embedded in the 3 direction of this right-handed SU2. Okay. So what happens though when the vacuum or the field phi relaxes into its vacuum configuration is that will break H. So in vacuum we have H as V divided by square root of 2 times the unity matrix, okay? So if I were to write my phi as a phi plus and a phi naught, then this phi C would be a phi naught star, phi plus minus, okay? So if I chose my vacuum expectation value to be aligned with this phi naught direction, it was real, okay? So that means in vacuum, I just pop a V in here, and I pop a V in here, so I get a diagonal representation of this H matrix. So you can see that this is really the case. Okay. So what happens now is, and that's just old school global symmetry breaking, is that we break down this H, this SU2 times SU2 symmetry, down to the diagonal subgroup. Okay. The vacuum will only be invariant under symmetry transformations where UL is equal to UR, because then you can just pop it through and you saturate it through the unitary condition of SU2 matrices. So that breaks UL to UR equals to UD. And if that was intact, okay, I erased the mass matrix, this means that all eigenvalues have to be identical, okay? This can only happen, and this diagonal representation of SU2 times SU2 can only be intact if all the mass values of the W fields are identical and the B field associated to that. So the only thing that can happen then is when you rotate the basis states, that these same eigenvalues that should sit on the diagonal, they just get mixed slightly, proportional to the cosine theta angle that you use to rotate into the mass eigenbasis. And this is, yeah? No, it will not. Because it's not exact. And I'll come to that in a second. But good point. And this is, you can take this as the first motivation of composite Higgs ideas. Okay? Because composite Higgs ideas sort of have this at their core. All right, where was I? Yeah, so if that diagonal thing is in state, is preserved, then that only works if all the mass eigenvalues before rotating are the same, and then this way the mass eigenvalues get just mixed by this cosine theta angle, which gives you exactly this relation then. All right, so this is referred to as custodial isospin. Okay, so for custodian and isospin, because we're dealing here with an additional 2. So this is custodial isospin. Yeah.
So you said if you rotate by some angle, like theta, then you rotate the mass eigenvalue.
Mm-hmm.
So does that mean that you can undo that and have some basis where all of them have the same mass? Or is that, did I misunderstand?
Yes and no. That relates to the fact that this is really, what we did here is we had a look at global symmetries in the Higgs sector. But now we gauge some of these global symmetries. And even worse, we are gauging a subgroup of the right-handed global symmetries. I said earlier that hypercharge, this U1, Y, you can embed in the 3 direction of UR. Yeah? That just gives you exactly the right quantum numbers that you want. So now if you gauge a subgroup, you explicitly break it. Yeah? And explicitly breaking it means that, of course, some of these nice features are lost. But you don't see this really at the classical level or the semi-classical level. But what this means is that this relation here will receive radiative corrections proportional to the order parameter that is related to the breaking of SU2R. And that order parameter is the gauge coupling G prime. Okay. G prime is small. So maybe I should have told you. I mean, you all know the W mass. What's the value of the W mass? 80, yeah. What's the Z mass or Z mass? 90. So we're very close to 1. Okay, so we're not dealing here with a huge angle, and that means that G prime has to be relatively small compared to G. This is actually the case. So this means that the breaking from gauging a subgroup is relatively small, so we would expect that this relation still holds very well. And that's also what we observe. And it's a twofold statement. First of all, it tells us that something nice is happening, and we probably deal with a doublet like symmetry breaking pattern. But also there's a tremendous success of perturbation theory, right? Because if you can calculate this to next to leading order, next to leading order, and it's bang on with experiment, then you know we'd live in a perturbative quantum field theory world, which is good news. But that threw me a little bit off what I wanted to say. Yeah.
So you showed the custodial symmetry by taking the Higgs doublet. So instead of the Higgs doublet, you had something like technical or some strong dynamics that makes the electric group. You still have, like, can you still get the rules?
Yeah. So if you deal with SU2s, then this always works. So
So you don't have to have a Higgs doublet, like that breaks the symmetry.
it works in Technicolor, but SU2s have to be some part of the flavor symmetry if you do this in Technicolor. So this was, if you SU3 color, is the prime example of Technicolor. So you in the unbroken phase, you have in 2 flavor massless QCD. You have SU2 times SU2 that gets Higgs down to a diagonal subgroup. You get the pions. And now you switch on the gauge fields, and you would exactly get that mass pattern because you start with an SU2 global symmetry, you weakly gauge a subgroup. And this is really also, where composite Higgs ideas and Technicolor are very related in that sense. And in a way, there is a contribution from the pions to the W mass, a very small one, but it's there. Yeah.
So we can embed U1 hypercharge into the T3 of the U1R or S22R. But I think in standalone we cannot exactly do that because the hypercharge, the standard particle cannot be always embedded into T3.
For
the combination of the T3R and
there is
another U1.
it's broken in the Yukawa sector as well. So this is why we'll talk about electroweak position measurements as well. So there are two major sources. So this would be related to what is called the T parameter. So you have this guy, okay, and deviations of this. You would write this as a 1 plus alpha T, where alpha is just the electromagnetic coupling constant or fine structure constant. And this T receives contributions from all areas where this breaking of SU2R occurs, and that's in the fermion sector, but also in the gauge sector. So we'll get to this in a moment's time, and if I don't fully answer your question, just make sure that I do. All right. So just to summarize this, this relation will receive radiative corrections. So mw squared divided by mz squared c theta squared will receive radiative corrections as SU2R is explicitly broken. Should be a bit more careful here, okay? Because mw squared and mz squared, they are observables, right? And they are input data to your theory. So this means you always have to think about this relation in terms of a comparison with a coupling relation. So it's really comparing renormalized quantities on the fermionic interaction side with renormalized quantities on the mass side. That might be input data to your renormalization procedure. And this is spelled out in this STU formalism, and we'll deal with that later on. Because this is what theorists really like, because it's a quick back of the envelope check whether your new physics model is really compatible with electroweak position data. Well, it's not compatible, but not immediately rule out, let's put it that way. All right, now with phi and phi z at our disposal, we can now also introduce fermion mass terms. Fermion mass terms. So fermions, we haven't really introduced that, but fermions are spinorial representations of the universal overlapping group of the Lorentz group. And because we're dealing with 4D, we can define this projector, or gamma 5, that maps out left and right-handed chiralities. So we can define psi L and psi R as 1 minus plus gamma 5 divided by 2 times psi. Okay, but this is a Dirac spinor. So it's a representation of the complex Clifford algebra. And these psi L are just representations of the even subalgebra. And that does not necessarily exist. So for instance, back in my days when I went to grad school, extra dimensions were really the dark matter of these days, so that was hot. And if you go to 5D, that gamma 5 is this representation in terms of a product with gamma naught, gamma 1, gamma 2, and gamma 3 times I. That's completely anti-commutating. So you already have found the Clifford algebra of a 5D theory. So in 5D, you don't have chirality. So that's, of course, an immense problem to get a chiral spectrum, because we see that the left-handed bottom quark couples different than the right-handed bottom quark. So people had to really work hard and orbifold all the unwanted states away from the theory. Okay, so this is already a strong statement that at least in our low energy theory, we deal with a perfectly four-dimensional world, unless you invoke special tricks. Okay. So Fermi theory really tells us how we have to assign charges here. Okay, so we can use this as a motivation to order the left-handed quark fields into doublets, UL, DL. So this is a 2, 1 divided by 6. UR and DR. They are singlets under SU2. We charge 2/3, so that will be completely saturated then by hypercharge. And 1 minus 1 divided by 3. And to some extent, okay, in the standard model, these charge assignments are completely arbitrary. So there's nothing that motivates the hypercharge assignment other than observing quarks exactly with that particular charge. Okay, I mean, there's a normally cancellation and so on and so forth, but you can also saturate this with other charge assignments. So when you deal with U1s in your theory, you always have this issue that you don't really know where the quantum numbers come from, and only if you absorb this quantum number into a nice SU5 theory, which is rank 4, you can make a meaning of how these charges really come about. So this is the quarks, the leptons, okay. New L, EL, it's a doublet again, minus 1/2, and the right-handed electron has one singlet and 1 minus 1, okay. And because I'm not a neutrino physicist, the right-handed neutrino stays out. So, one minus 1, yes. Yeah, exactly. Yeah. Sorry about that. All right, now with this, we can write down invariant bits and pieces for our Lagrangian at the mass dimension 4 level. So, for instance, we can generate down-type quark masses through interactions like this, YD. It's a Q bar L times phi times dr, okay? And so what I assume here is that these SU2 quantum numbers are implicitly saturated. Okay, so this is a 1x2 matrix, a 2x1 matrix, and you couple them together, and that just works. So if you now set phi to its vacuum expectation value plus emission conjugate, then you get a minus yd v divided by square root of 2 d bar L dr plus emission conjugate. Okay, and these are exactly the terms that show up in the Dirac-Lagrangian as a mass term. Okay, it's exactly mixing left and right-handedness. Okay, so we would identify this as the down quark mass, and this automatically tells you what the associated Yukawa coupling should be. So for the up sector, we can do the same thing, but we have to use, want to project out the upper component of the doublet, and we can do this with our phi c because that has the VEF in the upper component. So do this with that, and it's minus yu q bar L times phi c times ur plus emission conjugate, and again sending phi to its vacuum expectation value, we recover up type masses to u bar L ur plus hc. So all great. You get two things for the price of one in the standard model. You can generate fermion masses completely analogously to gauge boson masses. I mean, not really. The mechanism is slightly different, of course, but you can use the same field. This is really what I mean. And we don't really need to do that. And this is the whole idea of 2x doublet models and so on and so forth, that you can actually use a different pattern here of mass generation in the fermion sector compared to the gauge sector. And somehow they have to sort of conspire to make your S matrix unitary again, and we'll talk about this in a little bit as well. Okay, so in principle, of course, we deal here with the generation indices. Yeah, so up, down, Charms range, bottom, top. There are three copies of these guys here. So these Yukawa matrices, these Yukawa couplings really are 3x3 matrices, and so somehow we have to rotate them into the right basis where everything is diagonal to make sure that we deal with the mass eigenbasis, or deal with the fields in the mass eigenbasis. Okay. So the way this works, because we deal really here with completely different quantities. So UR can be rotated completely different than DR, yeah? And QL can be rotated completely differently than UR and DR. Okay, so we have a lot of freedom here to rotate stuff around, and our Lagrangian will not be sensitive to this. So you dress UL with a certain 3x3 unitary matrix, and you do the same trick for UR. Okay, so these are not related. You can essentially see that you can sandwich this between two unrelated SU3 transformations. So you have the freedom to do a bi-unitary transformation and completely nail these couplings down to a diagonal representation. Okay. So this works all perfectly fine. In this sector now, you need to worry about what happens really with the gauge interactions of these fermion fields. So of course, these have different gauge interactions because they are doublet under SU2 than, say, the singlet fields here. But because the Z mu and A mu interactions, they are essentially given by couplings to alpha, psi bar L, gamma mu, psi L plus beta, psi bar R, gamma mu. Psi R, okay, so whatever transformation I'll do here to the right-handed field will just be compensated by the complex conjugate transformation here on the other side. So the vector interaction does not really introduce a chirality flip, so we don't really see it in the neutral current interactions. So there are no flavor changing neutral currents in the standard model at tree level. The only thing where we could see something like this is when we mix up and down, and this happens in charge current interactions, because then we will see a net effect of the combination of a down type transformation for left-handed fields and a up type transformation of left-handed fields. And so W mu couples something like U bar L, gamma mu dl, okay, plus higher terms. So you can see if I rotate this and I rotate that, I will have, in the interaction term, I'll have some additional matrices that I need to worry about. Yeah? Not in the kinetic terms, because the kinetic terms will be completely diagonal, right? So, because there's no charge, so the charge needs to be somehow compensated in this interaction. So this charge current interaction receives fields, this basis transformation, and this is the CKM matrix. Okay. So has one complex phase and three angles, and that complex phase is the one source of CP violation that we see in the standard model. So now that we've introduced pretty much everything, we can fix our input parameters. And for this we have to pick experimental measurements. As I said, the terms in Lagrangian, they are not related in any way to physical observables, or not necessarily. So we have to really define a physical process from which we infer the underlying parameters of the Lagrangian as a bookkeeping quantity, if you wish. So we fix the input parameters. And there are various ways to do this. And of course, the precision of how you fix the input parameters will depend on how well certain processes are measured. One of the best measured processes that we have at our disposal is muon decay. Yeah, muons are abundant. So Feynman diagram for this is mu goes to a mu neutrino, spits out a W, and that W decays into an electron and electron antineutrino. Okay, so both these vertices are gauge vertices, so that comes with a weak coupling, that comes with a weak coupling, and because we know this from UA1 and UA2, MW is much, much bigger than MU. Essentially, there is no momentum transfer between these two lines. Okay, so we're completely dominated by the propagator suppression. I wrote down the propagator in unitary gauge for gauge bosons last time. So this will be suppressed. This will be suppressed by 1 divided by mw squared. Okay, so, and this is also the reason why Fermi theory is good, yeah? That we are dealing here with, as long as the momentum transfers that we are studying is much smaller than the W mass, then the four fermion interaction is a very good approximation. Okay, so what this really tells you is that you are measuring something here, it's called the Fermi Constant, and these factors here are just purely normalization. That's G squared times the inverse of 8 mw squared. Okay. If you go back now and have a look what the W mass is at tree level in relation to the vacuum expectation value in the weak coupling, you see that this is nothing else but the vacuum expectation value, 1 divided by 2 v squared. So just by looking at the muon decay, we can directly infer the value of our vacuum expectation value of the Higgs field. Okay, so from this, we know that V is root 2 times the Fermi constant times minus, well, to the power minus half. And this is the famous 246 GeV. So this is very precisely measured, and very precisely matched at tree level, because we have a very good understanding of the probability and the decay width of the muon. So from the Higgs sector calculation that we did earlier, we can also now fix everything in the Higgs sector. So earlier we had that v squared is actually a minus mu squared divided by 2 lambda. But we also know the value of the Higgs mass expressed in terms of these mu squareds and lambdas. That was a 2 v squared times lambda. So we can throw these things together and write down the potential of the Higgs field as an mh squared divided by 2 h squared plus an mh squared divided by 2v h cubed plus mh squared divided by v squared times h to the power of 4. So in the gauge sector, on top of the muon decay constant, so the Fermi constant, the only additional information that we needed after the Higgs, after the W and Z masses, was only the Higgs mass. Okay, so the Higgs mass in the standard model completely fixes the Higgs potential. Of course, if you start deforming the theory, then of course all these interactions can deviate from the standard model expectation, and we talk about this a little bit later. So this was really like after the discovery of the W's and Z's in 83, we had to wait another 30 years to find the one remaining ingredient that nailed it down entirely. Long wait. So now this is supposed to be Higgs physics, and so far we have not really done much Higgs physics. But as the dynamical field h of x fluctuates around v, we can directly read off the interaction terms with the gauge bosons and the fermions just by looking at the mass breaking patterns. Okay, so for instance, you look at mw squared, w plus mu, w minus mu. You express this in terms of the VEF, so you have g squared, v squared, divided by 2. W squared. Now you send this to g squared times v plus h squared divided by 2 w squared, where h is now the dynamical Higgs field, so that measures the fluctuation around the Higgs VEF. So you get back, when you do this, the mw squared W squared plus a G times GV divided by 2, W squared H plus a G squared divided by 2, W squared H squared. Okay. And you can see that this GV divided by 2, you can replace this by the W mass itself again. Okay, and this is what happens in spontaneous symmetry breaking. This always happens, that the Higgs interactions will be proportional to the mass of the gauge boson and the associated coupling. Okay, so can directly guess what will happen for the Z mass. It will be the square root of G squared plus a G prime squared times the Z mass. Okay, so in this way you can read off the Feynman rules for the Higgs interactions with the W's and the Z's. I'll show this next time. Are there any questions? Yeah?
Are there other doublets that you can use that are transform the same way as their
Well, you can throw in more than one. So that would be the 2x doublet model. For instance, you can add 3, add 4, add 5. Sky's the limit. But 2 is particularly motivated if you're interested in supersymmetry. Triplets are, just as an academic exercise, a little bit more interesting. Because if you write down just normal complex triplet, give that hypercharge 1, you end up with a doubly charged Higgs. So that's nice to see at the LHC, but at the same time you have the problem that typically you will not get the right WZ mass ratio. So if you only admit a single triplet, you're really in tension with electroweak precision measurements. But there are certain tricks you can play. So you enter back the old doublet, and you have a doublet and a triplet, and then you just parametrically suppress the vacuum expectation value from the triplet. So you fine-tune that to be small. Then you avoid issues with essentially exactly this WZ mass ratio. Okay, if that gets its mass predominantly from doublets, then you're okay, and you get a small deviation from the triplet. Now there are more sophisticated things. So Howard George I came up together with Makacek, where you have a real triplet, complex triplet, and a doublet, and that because that's actually, in a nutshell, it's relatively simple. Okay, if you have, so if you have a triplet, so you have chi1, chi2, chi3. What you want to do is you want to enhance the symmetry. They have your left-handed symmetry and a right-handed symmetry. If you only have a 3 vector, you can't do that. So you need to add 2 other fields. Okay, so you have an eta 1, 2, 3, and here you can maybe write the charge conjugated versions of these guys in here, right? And if you arrange this in a 3x3 matrix, you can again write down a triplet representation of left SU2 and right SU2, and you end up with a nice MW squared divided by MZ squared equals cosine theta squared. There is no free lunch because now you have a complex triplet, so this is a charge conjugate version here of that. So don't take this too seriously because there are signs and everything, okay? But you have a real triplet and you have a complex triplet, and their VEFs now need to be exactly the same for that to work out, right? Because in order to have custodial isospin, you need the vacuum expectation values here completely the same. So it needs to be related to the unity matrix. So somehow these need to be tuned. And what it turns out is that your quantum corrections, they will feel the presence. They can tell a difference between the real triplet and the complex triplet. So you introduce an additional fine-tuning in the T parameter. The T parameter measures exactly the deviation from the WZ mass ratio. And you calculate this, and it's done by Jack Gunyon and collaborators rather early on. You see that this introduces another quadratic dependence on whatever cutoff regulator you put in. So instead of solving a problem, you have actually created another one. So triplets are hard. And of course, you go to higher representations, it gets just more bonkers. Yeah.
Those triplets, do they have the same hypercharge?
So that's hypercharge 1 typically. So
Both.
yeah.
You mean just the complex one?
So the real one, I need to look that up, but I think it has. Yeah, that has hypercharge 0.
Okay.
So you end up with. That's why these things are phenomenologically interesting. We come to like processes for Higgs production and stuff like that later on. But if you have a doubly charged Higgs boson, and the triplet contributes to the mass generation of the W's, you will end up with terms where two same sign W's are coupled to a doubly charged Higgs. So you can see these things in same sign W decays. And of course, this is a fairly clean thing to see, because charge identification is very good in the leptonic final states of W's. So these are quite striking signatures, which are easily ruled out, and this is why experimentalists love them. Yeah.
Now, I guess naively thinking, I'd say that just the one complex triplet would only be able to break SU2 down to U1, so you'd have 2 U1s left over.
So if you can try it again. I can give you the triplet representation of SU2 generators, and you can run it through Mathematica. You'll see in the end that you have the same pattern. You break SU2, you retain quantum electrodynamics, but now your mass ratio of the W's and Z's is off by a factor of 2 compared to the SU2 doublet case. Yeah. You have to care about a lot of things when you fuff about with the Higgs sector. And so we're not going to talk about these effects here, but of course they are there. But what we're going to talk about is a lot of that stuff that relates to unitarity. So I said yesterday that this nonlinear realization of electroweak symmetry has nice features in the sense that you sort of almost can guess how higher orders should behave. And the Higgs mass as such is really a order parameter of the convergence of the electroweak series. And you can see effects of that left, right, and center. And a lot of search strategies at the LHC are really built around that. And so it really tests the fundamental fabric of perturbative quantum field theory in a spontaneously broken gauge theory. That's quite nice. But yeah, their constraints are plentiful, and we'll discuss some of them. Unfortunately, not that. Are we done? No? So we should be. So this means we have time for one more question. No? All right. Okay, thank you, guys.